modeling. There is a little bit of modeling here, and there might be interesting discussions on what type of software to use for this modeling. But anyway, so what I'm going to talk in this lecture is the drop formation and effects of interfacial phenomena on droplet formation in microfluidics, and the role of surface active agents. So just to put it a little bit into context, you've heard a lot about applications, and we started from two-phase flows. We looked at different flow patterns, and we spoke more about plug flow, and we will return to plug flow tomorrow because this is the flow pattern we mainly use when we do mass transfer in small channels. But what I am focusing today now is this regime, the droplet regime. And there are many reasons why this is an important regime. And again, you've heard some of these applications. But all these dispersions, we are interested in drops because we are interested in the dispersions, in drop dispersions, because they find applications in pharmaceuticals, in enhanced oil recovery. We use emulsions in the foods industry, in separation process as well, in printing, and yeah, and on all these areas. So in these areas, we use dispersions or emulsions. Emulsions are the stable dispersions that can stay, let's say, in this form for a long time. Usually when we say dispersions, it means that the phases might quickly separate if we don't apply some sort of force to keep them dispersed. So emulsions might have a form like this or this. Okay, lots of creams, mayonnaise, other food as well. But what we have started doing with the microfluidics is producing drops that are having very much a controlled size and very, very narrow size distribution. These are important actual parameters for the stability of the emulsions and also the feel, how they, what's the product, let's say, quality. And people have found out that with microfluidics, we can actually get these very, very nice, small, quite small or very small drops and a very narrow size distribution. And Shumana before just mentioned also some other applications we can go into, such as double emulsions. Printing is one area emulsions can be used, and so on. So when we want to have dispersions or emulsions, we do need, in the majority of cases, to add surfactants, okay? Because otherwise they're not going to stay stable. They're going to separate. Do people know what surfactants are, or surface active agents more generally? Yeah, it's molecules that like to attach at interfaces, and they are usually long polymeric. They are molecules that may have a long chain that is hydrophobic, and a head that tends to be hydrophilic. So that allows them to sit at the interfaces and in a way stabilize the drops. So when we have surfactants, of course, all these phenomena, these drop formation phenomena can become more complex. And this is what we are going to look a bit in this lecture. So again, a standard setup that we have used to start experimentally this drop formation. We talked a lot about experimental techniques yesterday. I won't go too much into it. You yourselves have done an experiment as well. So we have our pumps, microfluidic chip or channel or just tube, some imaging, some camera, and then different types of light, either backup, either just LED or lasers if we want to do something more fancy. This is, okay, has a lot of information, but this is actually a microchip, a chip we bought, and it's not quite circular. But we have used this for a lot of work, so a lot of the results I'll show you are based on this one. So a little bit about surfactants, and I mentioned those here, not that you can remember them, but just to show you a little bit what we are interested in when we are looking at surfactants. Some of the work I'll show you has used these three surfactants, SDS, DTAB, and this is Triton, TX100. Our aqueous phase was water. In some cases, we're adding glycerol because we're trying to bring the refractive indexes close to each other. And we used silicon oil as the organic phase in this case. If you can use different oils. Silicon oil we have found is a kind of easy to use, and by playing with we can find different silicon oils that have different viscosities and refractive index, and we can match those by adding glycerol and amounts of glycerol in the water. So for these studies, we've just used silicon oil. And you have here the various properties, but what I wanted to show you is that this behavior here. So we did our surface tension or interfacial tension measurement, and we got for the different surfactants, color-coded here, we got different behaviors. How much do they reduce the surface, the interfacial tension, and also where is the CMC? And the values here is the CMC values. So why is that interesting? And this is some of the, let's say, concepts that I'll try to introduce, is that the CMC for the different surfactants is different. So basically, these two, DTAB, the green and the red, are, let's say, higher, and the Triton here, the blue, is the smallest one. So this also affects, and we have found, and it has been shown that affects the kinetics. Let me see what I have here before I go to that one. Affects the kinetics of the surfactants moving to the interfaces. So I will have quite some equations and results, but this is the concept I would like to convey. Once the drops start forming, let's go to this nice one here. Here, even if we have the surfactant in one phase, there is no interface to go to. Okay, so the surfactant will start moving to the interface once it sees the other phase. So there is some dynamics happening here, and the phenomena are not steady state. There is a dynamic phenomena going on, because what we have is drops forming, have a certain time scale for that, and at the same time, surfactant races to go to the interface. And there is some discussion, and this is some of the results I'll show you, on how quickly does the surfactant end up in the surface, in the interface, compared to the drop formation time. Okay, so the concept I'm trying to introduce is that at this point here, where the interface is still fresh and the surfactant is trying to get there, we don't necessarily have the final surface tension, the equilibrium one, let's put it this way, but we have some transitional surface tension. Okay, and that's why the phenomena can be quite complex in a way, but you can think of it as the competition between two time scales. One time scale is how fast the drop forms, and the other time scale is how fast the surfactant goes to the interface. And the reason is that clear? I mean, this is the basic concept. And the reason we used these three surfactants was that this one in particular, the Triton, is a big molecule surfactant. And we saw that it has slow kinetics, let's put it this way. It takes longer to reach the interface. Okay, so we try to see if we, by using different surfactants, if we can get some results on what we are actually seeing. I will briefly go through that. Again, there are papers and there is a lot of work in the surfactants literature. If you get these curves, if you have these curves, you can actually use an isotherm. And this is this Longomirski-Shkovsky equation, which allows you, so this is the one that describes the interfacial tension and has these parameters here. This is the ratio of absorption to desorption of the surfactant to the surface. But it has this parameter here, this gamma, that we see it further down, that is what we call the surface coverage, which in effect is the concentration of surfactant on the interface now, not in the bulk. In the bulk is this C. But what happens at the interface? The concentration of the surfactant at the interface is not the same as the concentration in the bulk. And actually, even the units are different. So basically, by fitting this equation, with we can actually get this gamma, the concentration of the surfactant at the interface for different concentrations of the surfactant at the bulk, and the maximum value is what we are using here. So you have your previous data, you fit the data to the equation to get this sort of correlation. So what that gives us is, how does, if we have a certain bulk concentration, what's the equivalent concentration of the surfactant in the surface? Okay, this is the gamma. So a very quick calculation, this is like back of the envelope calculation, just to get some idea of the time scales I was telling you before. For example, for the Triton surfactant, TX100, the droplet formation time is, in some condition, is 6 milliseconds. Okay. We can calculate the diffusion of the surfactant to get to the surface concentration. So this is a correlation you can find in the literature, and this is that much. Okay, there are some assumptions, there are some numbers there. You may not have all for this for the whole surfactants. These are kind of common surfactants that are there. So this is the diffusion coefficient find. Okay, it's, as I said, back of the envelope calculations. That's what it's about. But in any case, give us a value of 35 milliseconds. What that tells us is that Triton is a big molecule, takes time to reach the interface, and actually it takes more time, according to these calculations, than the drop formation time. So this suggests that possibly when we form the droplets here, at least in the beginning, the droplets, or while this breakage happens, we may not have the equilibrium surfactant concentration. Okay, how much does this matter? We will see, we can see in a minute. But this is something that is actually, it just goes a little bit deeper on the physical phenomena that happens. And it might just be interesting to consider if people try to do simulations, because sometimes you just consider a constant surface interfacial tension, while what that suggests is that the kinetics of the surfactants, how the surfactants transport from the bulk to the interface, is also important. Maybe I should say here that the phenomena that are competing are this. This is simple processes, and we can it makes common sense. We know this is the way they happen. The surfactants are in the bulk. They have to make their way to the interface to diffuse. Okay, so it's a mass transfer. And then once they reach very close to here, very close to the interface, they have to absorb. Okay, so there are two steps. They have to reach the interface, mass transfer, absorb at the interface. The reach the interface is mass transfer, can be diffusion, depends on the mixing, is whatever mass transfer depends on. In this scale, we say it's diffusion. Once you reach the interface, to absorb to the interface, this depends on this constant here, the which shows the absorption desorption. Okay, and these times have to be compared with the droplet generation time. And you have a question.
So why go to CMC level? Can we
No, we don't have to. It's just that it gives you an idea of what sort of concentrations you have in the mixture. And what we have done also later on is that we use that to non-dimensionalize the concentrations. Otherwise, I mean, if I take a concentration here, for example, I know that these surfactants are below CMC, while in this case, I'm already above CMC, which means that the dynamics, the system is different. I may have my cells, I may have different kinetics.
to affect the interface and also at the different zones? Like in this case,
Yeah.
so
Yeah, fine.
so we want the same interfacial tension when we apply the surfactant, or we have
That's a different question. I don't know. It depends on what you want to do. But we found that what we can do is that to say that in all cases, at least, we work below or above CMC.
but it will affect your interfacial. Right?
But that's why we have different surfactants.
For SBS Indica, we are having nearly same interfacial tensions.
If you go vertical.
No, I mean, I think
Mhm.
CMC, they are nearly same.
Mhm.
Maintaining nearly same.
Yeah.
Same.
Correct. Yeah. So, but you see the difference later. You will see the difference in these surfactants. That's what I'm saying. That at least you can know that we use it. CMC means something specific. You have micelles forming, which means your kinetics will be different because now you have to release your molecules from the micelles to go to the interface. So if you start, but as I said, it depends on what study you want to do. For us, we use the CMC to know where we are in the concentration, let's say, space. We are below, we know there is no micelles. We're above, we know there is different. And we stayed below, okay, in this work. In other works, we have gone above, because in a lot of applications, actually, and going above CMC is actually very interesting from a research point of view. If people are interested for the future or whatever, because it's not as well studied, it's more complex phenomena, but at the same time, it's what most applications use. Most applications feed a lot of surfactant in the system to just make sure it's okay. Right. So very few things talking about flow patterns. Um, we talked about flow patterns in general in tubes. If we specifically look at drops, there is a lot of literature on that. I haven't put papers. If you go to some of the references I had before or after, you will see a lot of them mentioned. The regimes of droplet formation can be the squeezing, famous paper or very well quoted paper by Gerstecki et al. They discussed a lot the squeezing regime for bubble flows. It's the same. It's when actually the flows are slow, the bubble forms, the drop becomes very big. So the fluid at the back gets squeezed in a way and tries to push the drop forward. Dripping and jetting are the ones that are most commonly used for producing drops of a certain size. Dripping is like having a tap that drips. So your drop comes here, we'll discuss the steps, and then mud reach here, the neck breaks, and then the drop goes. Jetting is, depending on this is from experience, depending on the setup you have, the jetting can be a little bit more difficult to identify. So this is flow configuration. I don't think I mentioned. So we have the main phase, the dispersed phase coming here, and the two-side phase, the continuous phase comes from the sides. So in this case, your dispersed phase goes a little bit and then forms a jet that in the end breaks here to form the aqueous phase. We can have what we call threading, which is like annular flow. But a lot of people observe here, so it is possible further down that the front of the thread breaks. So it could be like a transitional one. And then there is this tip streaming regime that I'll show you in a map in a minute. It kind of appears at the very bottom of the map, and but you can have a look at it. What we have in, let's say, the dripping regime is these stages and in the jetting. So in the beginning, the dispersed phase appears and grows radially and axially, just grows as a drop. And then at some point, we observe this. So it comes here, it continues growing. But then at some point, we have this change in curvature. And the neck forms. This is the necking stage. So go from the expansion stage to the necking stage. So a slight change in curvature. And then in the end, here the neck breaks to give us the drop that detaches.
In the sea, it later on it's becoming similar to squeeze, if we see it later on.
No, what do you mean? No, this is no. Squeezing is very low flow rate. So if I go in the map, you will see that the squeezing regime disappears in bits. Okay. So this is a simple flow matter map, flow rate of the continuous and the dispersed phase. So the squeezing regime really appears very, very low flow rates. So this one, the dripping appears in this area of the map. Okay, this is our fluids. Of course, you can have different lines depending on different fluids. The jetting regime here. And you see the threading regime appears when we have high dispersed phase flow rate and low continuous. It's a bit like the annular flow in larger systems.
No, what
Mhm.
if from the later part, it seems that it is covering the whole dia, the bubble or the top,
Mhm.
and it is not completely round.
No, but that moves.
Yeah, so I mean, if you see later on, if you want
But
to
the squeezing refers to the generation.
yeah, I understand.
Yeah.
What I'm trying to say, if you look at the later part, then
Mhm.
you see
Mhm.
the squeezing and jetting will lead to the same formation. They will look like same, right?
They will form drops.
Similar to each other.
No, I think the sizes are also different, but this is something to compare.
And
Yeah.
then at the back, it seems
Yeah.
that there's another drop, which is
Yeah, there is, but I'm saying the sizes you form could be different between the two regimes. You mean if that is similar to that?
yeah. That drop is
Maybe,
standard.
yeah, maybe, but it's the different, the forces that cause it are not the same.
Yeah.
Yeah.
If the net result is same,
Yeah, what I'm saying is that we are looking at one case. I cannot generalize based on that. So I cannot generally tell you that these two regimes will end up in the same drop size. Okay, because the phenomena that cause them are different.
Right.
If they happen to be, they happen to be, but what causes them to break is not the same mechanism. Yeah. Okay, so that's what I was trying to say. Here is basically you block the fluid behind. In the jetting is more of instabilities that happen here. Yeah, and of course, yeah, I mean, I don't know if they would be generally the same or not. Yeah. So, okay, so this is what happens if we don't have any surfactant and we use that as our base case. And then we see what happens. So this is the, just try to now. Okay, and let me just reveal everything. When we add the surfactants. So what we get is that's what I about non-dimensionalizing the concentration. When we start adding surfactants, what we observe is that basically the dripping regime reduces. The area it occupies in the map reduces. So this is for surfactant, 0.2 of the CMC, more, and this is above CMC. And actually, in that case, we completely lose the squeezing regime. And just to say that when we have very high concentration, we also see this tip streaming here. And this is for the, if I can move that. Yeah. This is for the SDS surfactant. And yeah, we try to do that with the different surfactants. This is with the Triton. And okay, this comes back to your point. Here we used, the thing is Triton has quite low CMC. So if we wanted also to be in some concentrations in the phase that are similar to what we did with the other surfactants, we were going a lot above CMC. So when we have the low 0.1 CMC only, this is the reduction in the dripping regime area. And when we were increasing more, we're seeing the same decrease of the drip regime. And again, some tip streaming at the end. What I will try to do now is, and bear with me, I'm just introducing the concept as I said. You can go to the papers to look in more detail what we are doing here. Is we said that, okay, let's go to this one because it is a nice big figure. We said that once the dispersed phase joins the continuous phase, this is the configuration of our inlet. Surfactants will try to get to the interface. They will have to, if they're here, they will have to diffuse this distance. If there is any circulation patterns that will help the mass transfer, they reach here, then we have to have absorption. And at the same time, the more interface forms, more the drop is growing. So what we try to do, and then I'll go to that one. What we try to do is, can we somehow estimate what is the actual surface tension or interfacial tension when the drop is generated, rather than just using the equilibrium one? And that's how we went to do it. And remember this thing, that was our goal. Can we calculate the interfacial tension, or as we called it, the dynamic interfacial tension, because it's not the final one. So to do that, we needed, and I'll explain why, we needed to have some information on the drop size that forms. Okay. And if you've done any drop microfluidics, we discussed it a bit all these days as well. There is, and I will go back to that, but basically it has been found that the drop size does depend on the capillary force. Yeah, and you remember capillary, which is the competition between the viscous and the surface tension or interfacial tension forces. Okay, you could say that may come from a dimensional analysis. If we put down the parameters that are important, you will end up with a capillary number. And there has been some work, if you want to dig on that deeper, there are some efforts to calculate these, let's say, interfacial forces, and some efforts to calculate the viscous forces, effectively the drag force as the bubble forms, the drop forms. I won't go into detail, but these are, how can I say, mechanistic models. CFT will give you a better answer, a more detailed answer. But these are, let's say, models, analytical models, where you say, for example, the drag force will depend on a drag coefficient. Okay, how do you calculate the drag coefficient? You have not a solid body, you have this shape. But anyway, there are some suggestions on how to do this. But basically, these are the two main forces. And that's why the drop size we get depends on the capillary number. Yeah. And so then you can do a lot of work. And yeah, I mean, this shows you a little bit how the drop size changes. Can do work, we can get a lot of drop sizes from the different surfactants. As you expect, the drop size will decrease as we increase the continuous phase flow rates, more drag, okay? The velocity difference changes. As we increase the surfactant concentration, we will decrease the drop size. Again, we reduce the interfacial forces. This all makes sense. What we also found is that at the high concentrations, the sizes collapse. And we get the same with all the surfactants, the same behavior. Although with the Triton, the curves do not entirely collapse. And this to us indicated that perhaps for some conditions, Triton does not reach this equilibrium interfacial tension. Anyway, having all this data, we put them all together and we produce the correlation specific to the system. There are other correlations in the literature, but all of them depend on this capillary number. From our system, we developed this correlation for the average diameter, which you can see here now how it compares, how it looks. It's doing okay. Yeah, and we have the line, we have some, we know how good the fit is, but we have included all our data here and we got this line. So this line now gives us, at least for our system, if we know the conditions, the capillary number, and the ratios of flow rates, we can get the average drop size. This is one thing that's useful, but why we needed to look at it more? And just pay a little bit of attention to this idea. We wanted to know what is the dynamic interfacial tension when we create our drops. Okay. This graph tells us that the drop size depends on the capillary number. If we know if we know the drop size, we can calculate the capillary number. We can go back, we can do the inverse, let's say. And from that, we can calculate the gamma, the interfacial tension. Yeah, is that okay? Is that clear? So we did lots of experiments. We made a nice curve. And now we say, if we have this curve, can we use the drop size to actually calculate the capillary number and from that, the interfacial tension? So now, for all these experiments, to do that, of course, and this is the catch in a way, we have to create this correlation from data where the surface tension does not change when we create the drops. Otherwise, the dynamic effect is involved there. And of course, you can do that if you have pure fluids. Yeah. And it would be nice to just do it with pure fluids, but sometimes it's very difficult to get all these ranges of interfacial tensions, or to do it with surfactants, that, yeah, you have already, all your curves have collapsed, which means that your concentration in these cases at the interface has reached equilibrium. Okay, we either, saturate it, we make sure we put enough surfactant so the surface is entirely covered, and that's why has to be one value, the CMC value, the equivalent of the CMC value, or we use pure fluids. So there has been work in the literature, and that's an idea we worked a bit around, where people try to use different fluids. But as I said, you don't cover all, it's very difficult to get a wide range just with pure fluids of surface tension. Perhaps we try more. We mentioned aqueous biphasic systems. There are, but that's how we did it. So, okay, so now we actually now use the drop sizes to go backwards and to calculate the interfacial tensions. And what we see is that for the STS surfactant, which is considered the fast surfactant, because it's a small molecule, goes to the interface, absorbs fast, is that apart from the very, very low concentrations of the surfactant, in all other cases, we do reach okay, these are lines of the equilibrium, interfacial tension for different concentrations. We actually get down to equilibrium. So for STS, apart from the very low concentration, we can say that our surfactant concentration at the interface and the surface tension, the interfacial tension, has reached its equilibrium. Goes fast, the drop formation time doesn't quite affect it. So we could go and do simulations, for example, with this equilibrium value. And the same with the T-tab, and that's why the Triton is an interesting one, because actually, as you can see, this is the equilibrium values down here, and we are far away from them when we form the drops. So this is a nice insight we get by doing this work, and just shows how complex the phenomena are when we start having surfactants in the system, and very interesting as well. I won't go into that much on that because I think we will be confusing the message. But what I wanted to say is that, again, if you've done some chemical engineering or transport phenomena, what you can do before you go to all the detailed, let's say, parameters is just to compare times, as I did before. This is how long the diffusion time is. This is how long the drop takes to form. Compare these times. We compare these times and we see that actually we cannot reach equilibrium. Oh, yes, we can. And here what we did is just compare these some of the times, the absorption time and the diffusion time for the different surfactants, which kind of prove what we said about Triton, that is slow. What, though, I found more interesting is going back to this map. So here what we did, and this is because these dimensionless numbers worked, we talked a lot about flow pattern maps in the beginning. This is a map of the drop formation regimes. So we have here the dripping and the jetting regime. So all these yellow, orange are dripping, and the black ones are the jetting regime. We did this map with the capillary numbers, the continuous and the dispersed. What we found is that if we just drop all our data in, using as the equilibrium surface tension values, there is a bit of a confusion. We don't have clear boundaries between the two regimes. Okay. However, when we try to replot the map, but now using not the equilibrium interfacial tension values, but the gamma we calculated here, we saw that we managed to have a nice separation, which was nice. Because, as I said, this is comes from Christianity, it's the Holy Grail. When we do flow pattern maps, we really want to have coordinates that cover as many conditions as possible, where the boundaries between the different patterns are clear. Yeah, because this is like a reference. You can also fit a line, you can use it in some sort of modeling to say that above a capillary number of this, I have this regime, below I have this regime. You cannot do that here. Okay, so that's why, in a way, understanding how the surfactant transport works can help, for example, in this case, making a nice flow pattern map of the different regimes. And this is a general, as I say, it goes a little bit beyond. This is when you do flow pattern maps and you try to draw lines or to have the right coordinates. You have to, when you count the phenomena, then you can predict in a way a lot of different cases. Yeah, but if the maps are only for a specific system, then when you put data from another system, of course, there would be overlaps and everything. So this is the story of the dynamic, and also just to look a little bit at the physics behind the drop formation. And that's why simulations, we had a discussion in the break, can be interesting, but the simulations can also be quite demanding in that sense, because there is quite a bit of a phenomena involved. You have the surfactant being there, transporting, absorbing the interface, and a lot of that might require understanding that comes from other fields as well. How fast surfactants absorb at the interfaces. Okay, it needs to be studied. It's not clear. So for some standard ones exist, but again, if you have different surfactants, it's not given.
In the previous one, there's no data above this line, straight line. Why you have got this line? So
we should have cut it, you mean?
There's no data above this line. So
Yeah. No, maybe you could should have cut. I agree. Yeah. Yeah.
it requires a threshold that is deciding that from here on.
Yeah. Yeah, I guess if we go to the lab, we need to try to fill these areas for sure. Yeah.
Oh.
I won't stay too much on this one. There is everybody is doing a bit of machine learning these days, data-driven models, etc., etc. We did try to do it a little bit as well, and actually a lot of these things. That's what I've discovered. We were part of a large project in this work that involves some machine learning as well. And but you can do some easy data-driven models even with MATLAB. And so we had a go at it. What I can show you is that what you need is to have quite a few data, not huge amounts of data, numbers of data, but you need to have a few. So what we try to do in this case is to collect some work from a couple of different labs. So we had 468 data, different surfactants. So basically to predict the drop size from using a data-driven model. I won't go too much into it. I think what we learned from the whole experience is that when we try to collaborate with different people, it takes time to speak the same language. So that's again for future work, research, or whatever. We could be talking to our computer science colleagues saying self-extension, and would be like, whatever, could be anything. Or it can't be like that because you're above CMC. It didn't mean anything. So there was a lot of discussion in the beginning to actually fully communicate. But it was a nice experience. And you can get things. For example, in this case, we had the empirical model we developed, and that was the prediction. If we use the data-driven model, we had a slightly better prediction. So it's not bad. And there is, of course, a lot of things to be done, just showing it here. Some safety and some velocity sensitivity. I will go kind of quickly through that. We mentioned a few things like this when we were discussing yesterday the different measuring techniques. So what I wanted to show, this is what we had with the two-color paving. Here, I show them here because it's a nice figure we put together. Drop formation and increasing surfactant concentration. And it is kind of interesting to see how the velocities change when the surfactants start depositing on the interface. So here is a clear surface. We get nice circulation patterns. And you see how this changes at the different stages. Here when the neck forms, you kind of lose this circulation here and so on. Once I'll go to this case, we have a lot of surfactant. You can see now this thing behaves like a solid body, maybe. It just all moves forward with the same velocity. So it's actually quite interesting to get that experimentally. This suggests, even if you don't know that you have surfactants, that something has happened on the interface. It's interesting to see that entirely you lose this circulation because the surface is not mobile anymore. And some comparison again, because we had the imaging, high-speed imaging, the PIV for one case. Okay, clear system when we have little surfactant, high surfactant, and yeah, we got So what we try to do is to see if we used this more detailed data to kind of completely validate the CFD. And the reason we wanted to do that is because having validated the CFD for below CMC, then we could use the CFD to get information that is more difficult to get experimentally, which is where is the surfactants? Okay, how is the surfactant concentration in the bulk behaving? And how is the surfactant concentration at the surface behaving? This is very difficult information to get experimentally. There is some work in the literature with fluorescent surfactants. It's very, very difficult. You can get some results, but it is difficult to obtain experimentally. So actually to have this synergy between experiments and modeling can be good for understanding phenomena. And yeah, when we had very high surfactant concentration, we did have this accumulation of surfactants on the front. And there is a lot happening on the bulk as well, as you can see, because there are circulation patterns inside the drops. So that's how safety and experiments need to go hand by hand, especially when there are tricky phenomena involved. I will now, before, I have probably rushed through that, but any questions? Because there is one, I have a couple of slides on a slightly different topic, again about surface active agents and the drops.
And the concentration boundary layer is two different ways give the answer of this looking the concentration boundary layer.
The concentration in here, you mean? In here. So what happens is actually, and I kind of skipped on that because it's going a little bit deeper into the surfactant literature. When people try to evaluate, where am I? Do I have this correlation? Yeah. So there is in these not simpler equations, let's say the analytical equations, there is always the assumption that there is a film, a layer very close to the interface. So it's a bit like the two-film theory. So you have a very good mixing in the bulk, and then very close to the interface, there is a film where the surfactant moves from the to the interface. So it's depleted from there, and then surfactant from the bulk goes to this film. Yeah, so how there are some ways to calculate it. There is literature, and actually in one of the papers I've suggested there is some way, but these are all, it's a bit like the two-film theory. So there is some assumptions that this should be that thick. And indeed, if you can get more information on the actual from simulations, then you can start, I mean, obviously the surfactant concentration, the drop here is not uniform. So you cannot say that the bulk is uniform and there is only a film around it. But to do some calculations like this one I showed you here, you are based on this theory. And there are slightly different approaches. But yeah, yes, I mean, it's a mass transfer phenomenon. So there is the mass transfer, the transport phenomena, coupled with thermodynamics. And then there is the actual kinetics. Once you have your surfactant here, so how quickly is it absorbed? It's like how quickly does a reaction happen? This is that's why there are absorption kinetics or desorption kinetics. Yeah.
So the TX100 graph.
Yeah.
The reverse dia that is formed is same as the SDS and CMC.
Yeah. Where are you?
Previous one. Back, yeah.
Hmm.
Not this one, the back. Previous one.
Okay. Yeah.
So in this, the lowest dia is still the same like DTAB, whereas the interfacial tension it leads to is much less than DTAB and SMG. I mean, it should have impact on the average size when it is fully at CMC and beyond.
Yeah, it's not exactly the same. So the other thing I should say is that I don't know what sort of differences do you expect, okay? Because it's another point we found, there is local differences, let's say, but in this system, we probably got the sizes within a range. Yeah, it's not double, it's not half, it's a combination. It's yeah.
But I'm saying the lowest side
Yeah.
is still the same like DTAB, whereas the interfacial tension it caused is much lower than DTAB.
Yeah. So maybe the surface forces are not as important as it's a combination of different forces. I can't comment more on that. I can't say anything more. Yeah. So it's that, but brings a good point on if you want to study in detail and get precise answers, this might be relevant. What we found, and this is food for thought in my mind, is I skipped that, I went a bit quickly, but so we had all this data, same setup, and we did our data-driven model. And in the beginning, in the data-driven model, we put as inputs the two flow rates, the surface tension, and the concentration. Okay, and we got one model. We found out that when we omitted, I think when we omitted one of the two, the results were not very different. Okay, so as I said, it's a big field. It's still we're in a small area, but maybe that implies something within a certain error bar. Okay, because that's what I'm saying, and I think we had this discussion in the break. If you want to understand phenomena, to have precise answers is one thing. If you want to have some prediction within a certain within an uncertainty and accepting there would be an uncertainty, some simpler models like this one may be fine, but it does depend what you want. If you are interested in the application, I would say you can live with 3-4% uncertainty. As long as you know it's 3 or 4% and it's not 20%. But if you are trying to dig on the phenomena to understand what's the phenomena, because the phenomena leads to better predictions, then it's a different story. Yeah, so I would say with all these things, it's worth having in mind. I'm also looking a lot, we are also looking a lot at the application. And of course, this it's nice to have that in mind. Yeah, so I'll go very quickly to then. I have, not very quickly, but I have enough time to go and mention something else that I think is also very interesting, especially for the people that think for future research and projects. We've talked a lot about surfactants, and it's fine. They're used a lot. But surfactants, at least where I come from in the UK, there is a big discussion on moving away from oil-derived products and to also to have more sustainable materials and everything. A lot of the surfactants come from are oil-derived, and there is work to try to move to different types of surface active agents, and particles are one of them. Particles can be any particles, but the other interest comes from the fact that a lot of particles, I don't know if some of you might be working on with nanoparticles, small particles, can be bio-derived or can be biodegradable. So there is an incentive there to use these biodegradable, bio-derived particles for all the reasons I mentioned. The other thing that is interesting from, let's say, product functionality and from research point of view is that your particles are not just your hard polystyrene spheres. A lot of the modern particles are soft particles, or gels, or core shell particles. So they also have some elasticity. And of course, that opens up a lot of new areas, and a lot of people have started exploring them. Some of the particles can be stimuli responsive. You increase the temperature, you decrease the temperature, you increase the pH, you decrease the pH, you can change their size or elasticity. So there is a lot of things that can be going on.
Approximate particle size.
I have, let me show you in a minute. So this is a few things, some of them are from the literature as well. I'll show you what we did in a minute. And this is a schematic, basically. You can have this sort of particles. Particles, especially the soft ones, are made from polymers. They're not nice and spherical. If you go deeper, or depending on the type of particle, you have chains that can entangle, can form different formulations, and so on. What people have measured here is and this is, don't look at the numbers, just to see this effect. Have people here done any rheology at all? So, if you do rheological studies, rheometric studies, you can have the elastic and the loss modulus. One of them gives you the fluid-like behavior, the resistance to friction, to flow, let's say, and the other gives you the solid-like behavior. Okay, this is viscoelastic systems. And basically, if you get something like that, this is how much of the particle is behaving like a fluid, if it is in a solution, how much behaves like an elastic solid. So this shows that the particles have elasticity. And once we put the particles at the interface, now this is the behavior, the rheology of the interface. And you can see that the interface is elastic. So by putting the particles there, you are actually giving different properties to the interface, and it complicates the phenomena a lot more, because now, if we try to stretch the drop to detach it, your interface is elastic. How do you model that? What does that give you? Okay, so some properties of these particles is that we can change the functionality. They can be green. And they have improved stability on the coalescence. This is actually, once they absorb at the interface, the particles, it's not like surfactants, they won't dissolve. So they absorb irreversibly on the interface. Let me just show you everything here. Again, I won't go too much into this, but we actually, these are some of the particles we did. So we used some very standard NIPAM particles, microgels. The ones we used here had 160, that I'll show you, that had 165 nanometers size. I don't know why it is not here, but we also use some hard particles, polystyrene, and the surfactant, the STS we saw before, to see what we get. And here is some, what do you get? So it's the surface tension for the system we used. It was water and dodecaine. And you can see, okay, this is the interfacial tension. This is the interfacial tension with the gel particles, and this is with the STS. So, okay, the reduction in the interfacial tension is not as big, but of course there are different particles as well. And we also got this from the literature, this interfacial rheology. Let me just show you now a couple of interesting things on the formation. So we played, and this is a lot of work in progress, because we are continuing to work in this area, because it's very interesting. So we have these three different surface active agents, our STS, the surfactants, and two different particles, the polystyrene particles and the gel particles. So hard particles and soft ones. And what we have here is we just did the drop formation studies, and we got the drop size at different flow rates of the continuous phase. And I cannot remember now, I don't have it here, what's the dispersed phase flow rate, but it was comparable flow rates. And what we found is that these green lines is the results of the drop size from the surfactants. Okay, so in that case, we saw that as we increase the surfactant concentration, the drop size decreases. What we got with the particles is that we actually had one drop size, at least within this range of concentrations we studied. We didn't have, by changing the concentration, our drop size was 1. We didn't change. It didn't change. It was 1. It did not change. What we found, though, another interesting phenomenon is that when we looked at the transition from the dripping to the jetting regime, using again the surfactants and the particles, you remember what we said with the surfactants, as we increase the surfactant concentration, the regime becomes, the dripping regime shrinks, becomes smaller. So what we found is that when we have the polystyrene, the hard particles, so this is not minus and plus on concentration, just to show that this here is the hard particles, this here is the soft particles. When we add the polystyrene particles, the transition happens at higher dispersed phase flow rates. Right? When we add the soft particles, the transition happens at lower dispersed phase flow rates. So we didn't change the drop size, but we managed to tune the transition between the regimes. As I said, this is working on the go, in happening. And I did not include it here because I thought it would be too much. But it's also very interesting. We try to look a little bit at the dynamics when the drops break. And there you start seeing that actually having soft particles on the surface affects, as the drop breaks, affects the dynamics a lot. So again, it may not mean something too big in terms of what's the final drop size, but the local phenomena can be quite interesting. And as I said, this is the fundamentals. There is one of the promises, and people have been using them, of especially the soft particles, is to change their properties with external stimuli. If you change the temperature, they might shrink or to the pH. So this can affect, so in situ, you can actually affect how your particle or your interfacial properties change, which can lead to more or to less stable emulsions, for example, etc. Or maybe enhance. I mean, a lot of these things Professor Ghosh mentioned before can be used for drug delivery. There is a lot of ideas along these lines. And this is the last one about particles. Talking about particles, it allows you, the good thing with the particles is that although with the surfactants we have such trouble to try to see them, with particles a bit easier. So here we put some fluorescent dye in our napalm particles, and we try to see what happens with where do they go. And we had different sizes of these particles, small and large. So that's the ranges we worked. And an interesting phenomenon, let's say, was that the small particles sat very nicely. This is with a confocal microscope. And you can see they cover the drop very well. While the large particles have a bit of a patch behavior here, there seem to be some interconnections here and there. So looking at it, we would have thought, I would have thought, that this would be the more stable emulsion. Okay, what we found, though, is that this is actually the more stable emulsion. And it is possible this happens because stable means that coalescence doesn't happen or takes very long to happen. It is probably because these networks kind of keep the structure more stable and they don't allow coalescence to happen. But this is one of the effects, let's say, that in the end, if you want to make emulsions, these are the things that would need to be investigated. And this is, again, something that you can do. So different particle attributes like size, softness, elasticity can affect very much your final product. And just to open up more doors, there's a lot of people nowadays that look at particles that have different wettabilities. So they play with the wettability of the initial particle, but also they try to have particles that are half and half, let's say. Janus particles they are called, that are more, half of it is more hydrophobic, the other is more hydrophilic. So there is a lot into materials science that in the end can be useful for us as well. So I think I'm finished here and happy to answer questions.
So when we are injecting this microgel, let's say in the oil,